Today's lecture will be an introduction to capacitors, and in this first video we'll cover three aspects of them, and their physical appearance, the schematic symbol for them, and also we'll develop an intuition for how they behave in a circuit. Physically, there are three basic categories of through-hole capacitors. The first are ceramic. Ceramic are the smallest, both physically and in value of capacitance. They exist in capacitances from about 10 picofarads, and it doesn't really make sense to go much below 10 picofarads because that's starting to get to the capacitance of just two long wires next to each other. Up to about 1 microfarad is common. Oops, on picofarads I should have used a capital letter. Farad after Michael Faraday. These are often relatively high voltage, maybe 50 volts or 100 volts, and they're very inexpensive compared to our other two types. These are polyester film capacitors. These are medium, both in physical size and in value of capacitance. They have capacitances typically in the range of 1 nanofarad, which in electrical engineering, for reasons that escapes me, we usually call 0.001 microfarads, all the way up to about a large one would be 100 microfarads. Now these are somewhat inexpensive. These are bipolar, and so are ceramics. And by bipolar, I mean that there is no preferred positive side. They can be placed in either way. In fact, they look perfectly symmetric. And that's different than the largest of these, the electrolytics. Now, electrolytic capacitors are the largest. They're largest both physically and they're largest in value. They're available typically in ranges from about 1 microfarad up to, well, easily 1,000 microfarads and bigger. In fact, there are super capacitors that are available even in 1 farad and higher ranges. Electrolytics are the largest, and they are also unipolar. They have only one direction that they can be used, meaning one pin always has to be more positive and the other pin has to be more negative. You can see here that these are listed as having the more positive pin marked with a plus sign. Some types of electrolytics instead mark their more negative value. If you violate this and put a more negative voltage into the pin that's marked as it should be more positive, the capacitor will only tolerate that for a few seconds before it starts to break down. And it will change its capacitance, or it may even become no longer a capacitor. It may even become a short or an open inside. As an advanced topic, sometimes you're concerned about reliability. Ceramics and polyesters are both very reliable. If you create a circuit with them now, they'll still work 100 years from now. Electrolytics, though, use a paste, and that paste over time often will harden and no longer work. These are less reliable in the sense that even if you keep them in the proper polarity, after about 50 years, certainly after 100 years, I would no longer expect them to work. Luckily, that's far less time than most electronics will be useful. There are a number of schematic symbols used for capacitors. The most common in the ISO standard is this. For electrolytics, sometimes you'll see a symbol like this indicating which pin has to be more positive. Less commonly, you'll see an older symbol for a capacitor that has one curved plate, or alternatively for an electrolytic, one curved plate with a positive symbol. We've talked about the hydrodynamic model for electrical engineering circuits before. In this hydrodynamic model, a voltage source is represented by a pump. And in particular, a 6-volt voltage source might be represented by a pump that guarantees that one side is 6 psi higher than the other. And similarly, we represented current sources also as a pump, but in this pump, it guarantees that there is 2 gallons per second of water flowing from the bottom to the top. We talked about a hydrodynamic model for a resistor, which is a resistance to flow. And so in this resistance, there is some voltage pressure built up for a given amount of flow rate through it. For a capacitor, our intuition is a pipe with an impermeable rubber diaphragm stretching across it. And the intuition is that the more current that flows in, the more this diaphragm will bend, and therefore the more voltage pressure will develop across it. This is a better mental model than many others I've heard of, because it shows that as charge enters, the same amount of charge also leaves. It doesn't store a net amount of charge. What it does is it stores a charge differential. There's a positive maybe 1 gallon stored over here, and there's a negative 1 gallon stored over here. Total amount of net charge stored is 0, but that differential in charge inside has stretched that diaphragm, developing a strong voltage pressure. Let's use that mental model to see how the capacitor will behave in different common situations. Let's say there's a constant 6-volt voltage pressure source attached to a capacitor for a long time. What will happen to that capacitor? Well, here's our 6 psi pump. Clearly, that capacitor will be bent out of shape, and the amount by which it's bent out of shape will be enough until it pushes back with 6 psi worth of voltage. In other words, when this pump was first turned on and this capacitor was not charged up at all, it was initially flat. It had 0 volts across it. This would have caused water to flow, and as that water flowed, the capacitor would begin to charge up. It'd begin to distend and bow out, until finally it pushed back with 6 psi worth of voltage. And at that point, no more current would flow, because this is pushing this direction with 6 psi, this is pushing in this direction with 6 psi, and so you get 0 net current flow, and instead you just have a capacitor that has a certain amount of charge built up here, negative charge built down here, and no more current is flowing. Let's take another example. Let's say you've got a 4 milliamp current source, and it's pushing charge into a 2 millifarad capacitor. What does that look like? Well, now you've got a 4 gallon per second pump, and it is pushing charge, pushing current into this capacitor. And this capacitor starts out at time equals 0 flat, discharged, and there's no voltage across it. But after a short amount of time, it's pushed 4 gallons into it. So now it's pushed back, and it's going to develop some much larger than 0 voltage. And after another second, it'll have 8 gallons pushed into it, and it will develop an even bigger voltage. And if you plot that voltage versus time, it will look like this. Time, voltage across the capacitor, and you'll see it linearly increasing with time. Just like over here, if you plotted the voltage versus time, it would stay constant at 6 volts. The one last thing to develop about intuition is, what does the actual amount of capacitance mean? And the amount of capacitance in farads, think of the F meaning floppy. If you have a very, very large capacitance capacitor, think of a huge, gigantic floppy diaphragm, and it takes a lot of current in to make any appreciable voltage difference across it. In fact, because it's so huge, you can actually push quite a bit of charge into it without it developing much voltage difference across it at all. As an example of where you might find this useful, say you have an expensive car stereo system, and here's the 12-volt source of your car, and of course any real-world voltage source must have some sort of equivalent Thevenin resistance. This will likely be very, very low. This might be 0.1 ohm, say. In other words, the maximum current that can be delivered by this battery would be 12 divided by 0.1 ohms, or about 120 amps. That's great, except your deep bass thumping speaker might, right at the moment that it thumps, require more current than that. So, a very large capacitor, and by very large capacitor I'm talking about huge, maybe 2 farads or even 10 farads. These are gigantic thermos bottle-sized capacitors, are put in parallel. And now, over a period of time, this, which at 10 farads looks like a huge diameter rubber diaphragm, charges up to 12 volts. And because it's so huge, there's a very large amount of current that it can instantly provide to provide a huge bass thump, far more than the 120 amps that this could provide. And it can provide that very large amount of current for a small amount of time and not appreciably change the 12 volts across it. We'll provide a rigorous mathematical analysis of how much current this capacitor could provide for a short period of time when we cover the mathematical understanding of what capacitors do in the next video.